Hello, good morning, Corina. I hope you're fine. So today we are going to start waves. And in this topic, today we will learn traveling waves, wavelength, frequency, period, and wave speed, transverse and longitudinal waves, the nature of electromagnetic waves, and finally, the nature of sound waves. So we will try to cover these topics today. At the end of this topic, the students will be expected to derive the wave speed formula, so which is equal to frequency times wavelength. And students should be aware of order of magnitude of wavelengths of radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. So these rays are all electromagnetic waves. And we should know the position of these waves in electromagnetic spectrum. And in the data booklet, physics data booklet, so you will be given the speed of wavelength. The speed of wavelength is equal to frequency times wavelength. So let's start from traveling waves. Consider a taut rope which is anchored securely at a table. So we have a tight rope, and we will fix that rope to end of a table. And the end of table is here. We have tight taut rope here. So we can send a single wave pulse through the rope by moving your hand up and down exactly once. So when we hold the end of spring or end of rope and move it up and down once, so we will be able to send one signal. So let's see how it's done. See, by moving our hand up and down, we are able to produce a single wave. Or you can repeat the motion to produce a continuous traveling wave. If we just keep moving our hand up and down, so we will produce a continuous traveling wave like this. So we call these types of waves as traveling waves. So not that the rope as a whole doesn't go to the right. The rope particles just vibrate up and down locally. Actually, nothing is moving to the right. As it said, just the particles on the rope are moving up and down. They do oscillations. They just keep moving between two fixed points. If we look at this particle on the rope, so all particles on the rope are moving in this way. They keep oscillating between two fixed points. Depends on the amplitude of the wave. They're not moving to the left or right. Just all particles are moving up and down. It's very important because we will have this kind of questions in exam. So let's continue. We can use a spring instead of a rope. We can use spring, rope, string, any tight material is going to do the same thing. So if we use spring, you can send a single wave pulse through the spring by moving your hand forward and backward exactly once. So in the previous example, we move our hand up and down, but now we will move forward and backward. So it will be different type of wave. So let's see how the wave is going to be. Yeah, so we produce a single wave by pushing our hand forward and backward. Or you can repeat the motion to produce a continuous traveling wave. If you keep moving your hand forward and backward, So we will produce a continuous traveling wave. So let's see how it's done. Yeah, see, these are the waves. Now we will see the different types of waves. That's why these are very important. So for example, when we move our hand up and down, it's going to be a different type of wave. And when we move our hand forward and backward, it's going to be another type of wave. So we will see the definition soon. Note that the spring as a whole doesn't travel to the right. The spring particles just vibrate left and right locally. Yeah, in this example, the particles on the spring just moving right and left. They're not traveling. They just vibrate between two fixed points, as in the previous one. In the previous one, the particles were moving up and down, but in this one, the particles are moving right and left. All particles do oscillations, moving between two fixed points. See, like this. So when the particles move in this way, it looks like the spring or rope is moving to the right. Oh, but it doesn't. Just the particles are vibrating to the left and right. Okay, let's continue. Traveling waves energy transfer. Consider a securely anchored taut rope. So again, we have a rope. If we send a wave pulse through the rope, we see that when it reaches the end, it can do work on the mass. So let's send a signal. Let's send a wave pulse to the right side, and we will see what happens to the mass at the end of the spring. Note that in this case, work was done against gravity in the form of an increase in the gravitational potential energy of the mass. Yeah, so by sending a wave pulse, we are able to do work on the mass. We increase the gravitational potential energy of the mass, so it can do work. From this easy and clear example, we can say that the waves transfer energy. So you can think of energy being transferred from your hand to the mass via the momentum or kinetic energy of the particles while they vibrate. And now we will see the different types of waves, and these names will be really important. So we have two different types of waves, transverse and longitudinal waves. So let's see these definitions. Both the rope and spring were examples of traveling waves, and both traveled in the x direction. We call the material through which a wave propagates the medium. So far, we have seen examples of two mediums, rope and spring steel. Okay, this definition is also important. We call the material through which a wave propagates the medium. So we need medium for waves to travel, not for all waves, we will see soon, but some waves we need medium for waves to travel. That definition is important. The rope transferred its wave pulses by vibrations which were perpendicular to the direction of the wave velocity. The rope transferred its wave pulses by vibrations which were perpendicular to the direction of wave velocity. And we can see that direction of wave velocity is to the right side. But when we move our hand up and down, the vibrations are going to be on the y plane. So that means up and down. So Now we will have the definition here. Yeah, definition. Any wave produced by vibrations perpendicular to the wave direction is called transverse wave. It's the first type of wave. Definition of transverse wave. So what we do, if the direction of wave travel and the direction of vibrations are perpendicular, so this wave is always transverse wave. Now let's go to the second definition, longitudinal wave. So we keep in our mind, transverse wave means the vibrations and direction of wave velocity are perpendicular to each other. So the spring transfers its wave pulses by vibrations which were parallel to the direction of wave velocity. So when we move our hand forward and backward, so let's see what we have. So we have seen that when we move our hand forward and backward, the vibrations are to the left and right. And the direction of wave velocity is what? Also to the right. So that means these two directions are parallel. So when we have the parallel directions, so that means these types of waves are going to be longitudinal wave. So let's see, direction of wave velocity to the right side, direction of particle vibrations to the left and right. And these two directions are parallel to each other. So in this case, this type of waves are called longitudinal waves. See, the red arrow and blue arrow are in parallel. So any wave produced by vibrations parallel to the wave direction is called a longitudinal wave. It's very important definitions. Transverse waves and longitudinal waves. Okay, let's continue. Now we have one example. Practice. Categorize a water wave as transverse or as longitudinal. So we will see the water waves are going to be what kind of waves? They're going to fit in the transverse wave definition or longitudinal wave definition. So let's see. So if you have ever been fishing and used a bobber, you should know the answer. So let's assume we are fishing and we have a bobber. So when we have wave on the river or on the sea, on the ocean, doesn't matter.
Yes, just swimming with bow-legged women.
Yeah, we have seen many times this bobber is going to move up and down. So when we have vibrations up and down and the direction of wave velocity is to the left or right, these two directions will be perpendicular. So that means the water waves are going to be transverse waves. Yeah, firstly, the wave velocity is to the left side, given. And secondly, the bobber vibrates up and down. So the water particles vibrate up and down. And the angle between the wave velocity and vibrations are 90 degrees. So that's why water waves are transverse waves. So that again, the transverse waves are perpendicular to the wave velocity. Okay, now we will see the nature of sound waves. Now we have seen that the water waves are transverse waves. So what about sound waves? Example. Consider a speaker cone which is vibrating due to electrical input in the form of music. As the cone pushes outward, it squishes air molecules together in a process called compression. Actually, if you look at the speaker cone, we can easily see that motion is similar to the motion when we move our hand forward and backward. It's very similar. So that means we can clearly see that the sound waves are longitudinal waves. And we will see many types of questions while studying wave motion. And we should just keep in our mind that we will only deal with one type of longitudinal wave, which is sound. So if we have any question, which of them are given below our longitudinal wave, just we will have one answer, which is equal to sound waves. So the rest is going to be all transverse waves. It's very important. We will just deal with one type of longitudinal wave. So when we have seen longitudinal waves, so that means it's going to be sound waves, okay? The sound waves are longitudinal waves. It's very important. We will see that one a lot. So let's continue. As the cone retracts, it separates the air molecules in a process called rarefaction. So in sound waves, we will have compression and rarefaction. So generally in longitudinal waves, we will see these two definitions, compression and rarefaction. So if we look at the air molecules, these air molecules are pushed or move back, and we will have some different area. When we have more air molecules together, so we call that one compression area. But when we have less air molecules together, so we call that one rarefaction. And the direction of wave velocity to the left side. And we can clearly see that direction of vibrations of air molecules to the left and right. So these two directions are parallel, and we can easily say that the sound waves are longitudinal waves. Yeah, since the vibrations are parallel to the wave velocity, the sound is a longitudinal wave. As we said, when we have air molecules closer to each other, this area is called as compression. But when we have air molecules away from each other, so we call that one rarefaction. Okay, now we will see some more definitions related to wave properties. These definitions are very, very important. We should always remember these definitions. And we will start with crest and troughs. So let's see what's crest and troughs. Compare the waves traveling through the mediums of rope and spring. And we said that when we move our hand up and down, so we will be able to produce a transverse wave. And in the second one, again, we have in the second one, again, we have another spring. When we move our hand forward and backward, so we will be able to produce a longitudinal wave, like this. And on the wave, the peak points are called as crest. Okay, here is the crest. Definition of crest. The peak points on a wave are called as crest. And the lower points on a wave are called trough. These points, all of them are trough. Now, the crests and troughs are for transverse waves. What about longitudinal waves? So in longitudinal waves, we will have compression. So when we have the particles or springs loops are very close to each other, so it's compression. But when these springs or particles are away from each other, this area will be called rarefaction. Compression, rarefaction, crest and trough. But in many type of the questions, probably 90–95% of the questions will be related to transverse wave. So that means we will deal with crest and troughs rather than compression and rarefaction. So let's continue. Now, explaining the motion of particles of a medium. Here is an animation of transverse wave motion created by placing each of the blue particles of the medium in a simple harmonic motion. So let's assume that we have a rope or spring, doesn't matter. So when we move one end of the spring or rope up and down, so we will produce transverse wave. Now let's assume these rope or springs consist of many particles, and we will show these particles by blue circles. And let's see how these particles are moving in transverse wave. If you look at the wave, if you look at the blue circles, all blue circles are moving up and down. So they do actually simple harmonic motion. And another name for that one, they do actually oscillation. The oscillation means when we have any object, any particle, and if these objects are moving between two fixed points, so it's called oscillation. So if you look at all particles, actually all particles are moving between this point and this point. They just keep moving. So let's see again. See, all particles in the medium, this medium could be rope or spring, okay? All of them, all particles are moving up and down. The vibrations are up and down. So as you watch the animation, note that each particle has the same period. So what was the meaning of period? The period is the time needed for an object to oscillate one complete cycle. So that means if we measure the time for any particles moving between two green dots, all of them will have the same period. That means all particles will spend the same time to travel from one blue dot, goes to another one and come back. So we call that one as period. So let's look at the period again. If we look at this particle on the left, okay, so for period, the blue circle goes top and come back. So we call that one as one period. And the time needed to do one complete oscillation is called period. So let's say the blue dot goes to the next blue dot in 2 seconds, let's say 2 seconds. And it needs another 2 seconds to move from top to the bottom. And altogether will be what? 4 seconds. So we can easily say that the period of this particle or period of this wave is equal to 4 seconds. Okay, it goes up and come back to the same point. So it's called one complete oscillation. And the period is the time needed for one complete oscillation. And all particles in transverse wave have the same period. It's very important property. So each particle is slightly out of phase. So what does it mean? While they're traveling up and down, they're not on the same X horizontal position. For example, let's look at the first two particles on the left, the first one, second one. When they are moving up and down, they are not on the same level. For example, while going up, while going up, the second particle is in front. While going down, and the second particle again in front. They are not on the same level. They are not at the same time moving up and down. So we call that one out of phase. And the wave crest appears to be moving left. If we look at the particle's vibration, it looks like the crest, wave crest, is moving to the left side. Yeah. If we look at the particles on the right side, it moves up and down. While moving up and down, all particles moving up and down, it looks like the crest is moving to the left side. Okay. Okay, let's continue. Explaining the motion of particles of a medium. So we are just dealing with the particles in a medium. And these particles could be, this medium could be rope or spring. Now we are dealing with transverse and longitudinal waves, and we are looking at the spring and rope. And the medium could be also what? Could be also water, or could be also air. So these are also mediums. Okay, consider a snapshot of the following identical mass spring systems, each of which is oscillating at the same period as the systems to the right. So let's look at. Okay, now we have a mass. It's doing simple harmonic motion. So that means it oscillates between two fixed points. Again, the fixed points are what? Here and here, here. Okay, so we can clearly see that. The object oscillating between these two red points, fixed points, it goes up and down. And if we take loss of photo, if we take a snapshot, so we will have this kind of photo, this kind of snapshot we will have. So that means if you look at here, when the time is 0, the mass is going up slowly. Then when it reaches the top, it's going down, comes to the equilibrium position, goes down, and the motion repeats itself, okay? So, for example, while moving between two red points, if we take the middle point of these two, it's going to be somewhere here, okay? And we call that point as equilibrium line, okay? Equilibrium line or equilibrium point. So this point is going to be on the graph here, same thing. So that red line is equilibrium point or equilibrium line. So actually the waves and the simple harmonic motions are very similar because we know that all particles in the medium do simple harmonic motion. So what does it mean? They move between two fixed points up and down. All particles do the same thing in the same period. So now we will have some more definitions related to waves. So at each position x and at each position x, we have excuse me. At each position x, we have a different value of y. So let's see what does it mean. For example, if we look at the particle at that position, we call that one as x1. And if you look at any other particle at any other time, let's call this one is going to be x2. So they have different positions, x1 and x2. And for each x, we will have different y. For example, for x1, the y is going to be 0. So that means equilibrium. But for x2, so y is going to be maximum amplitude. So we will see what's amplitude and what is equilibrium. So let's continue. And the systems at x1 and x2 are 1/4 cycle out of phase. So what does mean out of phase? We will see that definition a lot, that word a lot. What does mean out of phase? So out of phase means, so if we look at the points x1 and x2, okay? And we said that when the object's doing simple harmonic motion, okay, it oscillates between points A and B, okay? And we said that if the object goes from A to B and come back to the same point A, we said that it's one complete oscillation, one complete oscillation, one complete oscillation. Yeah, so if we divide the one complete oscillation into the two parts, for example, while the object goes from point A to point B, it's going to be what? It's going to be half oscillation. So that blue line will be half oscillation, okay? And again, if you divide the half oscillation in two parts, so that means from point A to middle point, let's say here, it's going to be what? It's going to be 1/4 oscillation. So, and if you look at the positions of x1 and x2 for y planes, because the oscillation happens on y plane, okay? The vibrations happen on y plane. All particles are moving up and down. So if you look at the particles at x1 and x2 for y plane, we can clearly see that between these 2 points, that point and that point is clearly what? The 1/4 cycle, the out of phase. If they are on the same line like this, they will be in phase. But there's a distance between these two particles on the y plane. So, and that distance is equal to 1/4 cycle. And we call that one 1/4 cycle out of phase. So we will have more examples related to out of phase and in phase. So we will just look at the oscillations. One complete oscillation is called what? One cycle. And if you take the half of one complete oscillation from A to B, it will be half. And again, if you take half of half oscillation, it's going to be 1/4 oscillation. And if you look at the positions for x1 and x2 on the y plane, so they are clearly will be at this point, this and this. And we know that that point is equal to what? It's equal to 1/4 cycle out of phase. Okay, let's continue. Now we see the same system a short time later. So T1 from the last slide, just we have seen. And now T2 a short time later. So if you look at the positions of particles at x1 and x2, see the x1 after some time, after t time, a short time later, it goes down. And x2, again, it goes down. Actually, by looking at these two graphs, we can say that the wave is traveling to the left or right. And let's see how it happens. The mass at x1 has gone lower. Yeah, we said it. The mass at x2 has gone lower too. Yeah, right. Which way does it appear the wave is traveling? Left or right? So to understand which way the wave is traveling, to the left or right, so we should draw the waves. So let's draw. In the first picture, the wave picture is going to be like this. In the first graph, we have the purple waves. If we move that graph and combine with the second graph, it's going to be like this. Now I'm going to do the same thing for second graph. So that wave belongs to, the purple wave belongs to the first one. If we draw the wave for the second one in green, it will be like this. And from here, we can clearly see that the purple wave in the first one looks like moving to the right side, because if you look at the green one, it moves to the right side. So we can say that the wave is traveling to the right side. Yeah. Now we will see some definitions: displacement and amplitude. If we look at either of the graphs, we can define the various wave characteristics. Well, so let's define them. The sign distance from the equilibrium position is called the displacement. In this graph, it would be the y value. So when we look at the graph at any time, the values on the y plane are going to show us displacement of the particle from equilibrium line. How many centimeter or how many meter it moves up and down. So for displacement of the particle, we should always look at y plane. At the horizontal coordinate of x1 along the length of the wave train, we see that its displacement is y. For example, in this picture, it's negative. Whereas at x2, we see that y is positive. So if you look at here, the position of particle here, it has negative displacement. Why? Because here is 0. The below 0 is going to be negative. But if you look at x2, at this position, the object has what? The object has the positive displacement. These are important. Yeah. So the amplitude is the maximum displacement. The amplitude is just the distance from crest to equilibrium position. It's very important definition. We will see amplitude a lot. And amplitude means maximum displacement of particles from equilibrium line. Again, to find amplitude in a wave, we should just look at the y plane. For example, in this graph, amplitude is going to be here, the maximum displacement from equilibrium position. And again, we can find the amplitude by looking at crest or trough, doesn't matter. It's going to give us same value. For example, from equilibrium position to maximum displacement, equilibrium line to crest, it's what? Amplitude, A. But we can find the A also from here, from equilibrium line to trough. That A is going to be also same value. Just the sign is going to be different, but don't worry about sign. We will ignore the sign. This point, let's say, for example, 2 meter, is going to be same as that point, 2 meter, but just negative. And for amplitude, we will just neglect a negative sign. Let's continue. The period and wavelength, another definition. So we have seen displacement and amplitude. Now the period and wavelength. The length in the horizontal dimension over which a wave repeats itself is called the wavelength, represented with symbol lambda, Greek lambda. And the wavelength lambda is the distance from crest to crest or trough to trough. Very easy definition. So if you want to find the wavelength of a wave on a given graph, we should just look at the distance between crest and crest or trough and trough. We just look at consecutive trough and consecutive crest. For example, between two crests, so it's going to be lambda wavelength, or between two trough, from trough to trough, again it's going to be lambda. The both of them will give us the same value. We can use crest to crest or trough to trough, it doesn't matter. Okay, the period, we'll show the period T, is the time it takes a wave crest to travel exactly one wavelength. The period T is the time it takes a wave crest to travel exactly one wavelength. Okay, it's going to be the period. Or we can say that when the particles complete one oscillation, it's going to be also what? Wave. The time needed for one complete oscillation is also called period. Or the period T is the time it takes a wave crest to travel exactly one wavelength. We will have examples and it will be more clear. The period is the same for all particles of the medium. And the next definition, wave speed and frequency. The speed at which a crest is moving is called wave speed. This is really a measure of rate at which a disturbance can travel through a medium. Since the time it takes a crest to move one complete wavelength is one period, the relation between speed, wavelength, and period is the speed of a wave is equal to lambda divided by period, or lambda times frequency, same thing. Finally, frequency F measures how many wave crests per second pass a given point and is measured in cycles per second, or hertz. Again, we have seen that before. The frequency is equal to 1 over period. And if you place frequency in this equation, 1 over period is equal to frequency, we can also use this equation. Let's write it down. If the frequency is equal to 1 over period, this equation could be also the speed is equal to wavelength times frequency. Both of them right, because the frequency is equal to what? 1 over period. If you write instead of 1 over period instead of frequency, we will have this equation. Both of them same. We may use both of them, depends on the given values in the question. Okay, the frequency means the number of oscillations in 1 second, or how many wave crests per second pass a given point. How many wave crests per second pass a given point. How many crests is passing a point in 1 second is called as frequency. Now we will have some problems, some questions to apply these definitions. So let's see. Practice. A spring is moved in simple harmonic motion by the hand as shown. The hand moves through one complete cycle in 0.25 seconds. So that means the hand is moving forward and backward in 0.25 seconds. A metric ruler is placed beside the waveform, like this. And the question is, what is the wavelength? Okay, to find the wavelength in a longitudinal wave, we should look at the distance between two compression or two rarefaction. So we have ruler, we can easily define the distance between two compression. So let's look at, if you look at the spring on the right side here, the end of compression is here, and end of the previous compression is here. So it's going to give us what? It's going to give us wavelength. If we look at that value, it's going to be approximately 4.7 centimeter. So the wavelength is going to be equal to 4.7 centimeter. And if we change into the meter, it will be 0.047 meter. So we have found wavelength. Second question, what is period? Actually, the frequency is given, and by using that information, we can easily find period. So the hand moves through one complete cycle in 0.25 seconds. So it's going to be the period. What was the definition of period? The period is the time needed for one complete oscillation, one complete cycle. So it's saying that it's equal to 0.25 seconds. So the period will be 0.25 seconds. And next question, what is the wave speed? So for wave speed, we can use the equation wave speed is equal to the lambda divided by period. So 0.047 divided by 0.25, it's going to be equal to 0.19 meter per second. And we should be careful about the units. And again, the unit of lambda was wavelength, must be always in meter. And the unit of period, time, must be always in second. And the unit of speed is going to be what? Meter per second. These units are important. For example, in the first one, question was, what is wavelength? And we have found as 4.7 centimeter. So in the equation, I couldn't use 4.7. Why? Because the wavelength unit must be always in meter. So that's why we have changed into the meter. So let's continue. Another question. Example, graph 1 shows the variation with time t of the displacement d of a traveling wave. So we are given two different graphs. In graph 1, if we look at y-plane, it shows displacement. If we look at x-plane, it shows time in second. Graph 2 shows the variation with distance x along the same wave of its displacement d. If we look at graph 2, we are given displacement on the y-plane and again displacement on the x-plane. So displacement on the y-plane shows the positions of particles and the displacement on the x-plane shows how many centimeter or meter the wave travels. So let's look at the questions. First question, use the graphs to determine the amplitude of the wave motion. So the first one is very, very easy. To get amplitude, we can use either of the graph. Both of them are going to give us amplitude. And we said that amplitude is going to be the maximum displacement from equilibrium position. So the distance between equilibrium position to the crest or to the trough is going to give us amplitude. So in this example, from the one of the graphs, the amplitude is going to be equal to 4 millimeter. Why? Because the unit on y-plane is given as millimeter. So let's look at amplitude. The amplitude, the maximum displacement is 0.004 meter. Why? Because we said the unit on the y-plane given as millimeter, so we have to change into the meter. It will be 0.04 meter or 4 millimeter. Here's going to give us amplitude. So both graphs gives the correct amplitude. Second question, use the graphs to determine the wavelength. Okay, to find wavelength, which graph must be used, first or second? If we look at the definition of wavelength, the wavelength is the distance between two crests or two troughs. So to find the distance between two crests or two troughs, we need values, we need some distance, some positions on the x-plane. So if you look at the graph, we have distance or positions on the second graph for x-plane. Let's look at. On the first graph, the time axis shows, the x-axis shows time. So that means we couldn't find wavelength for this one because what was the wavelength? The wavelength is the distance between two crests, here and here. So that distance is going to be here. But if we look at the x-plane, it's not the distance, it's time. So that means I cannot use first graph to find wavelength. So I should use a second graph to find wavelength. Why? Because if you look at the second graph, x-axis given in centimeter, it shows position, it shows distance. So again, the wavelength is the distance between two crests or two troughs, or the wavelength is the distance between one complete oscillation. So one complete oscillation starts from here and ends here. It's one complete wavelength. And the distance between these 2 points will what? It's given as 24 centimeter. So that means wavelength will be 24 centimeter. That's all. Is it 24 or 2.4? Probably 2.4. We will see now. Okay, the wavelength is measured in meters and it's the length of a complete wave. So it's 2.4 centimeter. So that distance is going to give us wavelength, which is equal to 2.4 centimeter. And if we change into the meter, 0.024 meter will be. Okay, it's the wavelength. Next question, use the graphs to determine the period. Now, the period is what? The period is the time it takes for one complete oscillation. So again, if we need time, we should use first graph, because in the second graph, there is no time axis. If you look at the y-plane, it's distance. If you look at the x-plane, it's distance. So that means I cannot use second graph. To get period, I have to use first graph. And I'll look at the distance between two crests or two trough. Why? Because it shows one complete wavelength. And it shows the time for wavelength. So let's check. The period is measured in seconds, and it's the time for one complete wave. So if you look at one complete wave, it starts from here till here, which is equal to 0.3 seconds. Actually, we can get the 0.3 second in the same way from here, between two crests, here, same thing. If we look at these two values, let's say here, what is the value here? If here is 0.1, but in this way, it's not going to be clear because it's not going to be easy to read values. But again, if you take these 2 points, it will be the same value. Okay, so if you take this one here, it's going to give us again 0.3 second. But easiest way, we should look at one complete wave, and one complete wave will start from here. In one complete wave, we have one complete crest and one complete trough. That's all. From that point to this point shows one complete wave, one complete oscillation. So the time is going to start from here till here, which is equal to 0.3 second. Next one, use the graphs to find frequency. Actually, we don't need to use graphs to find frequency because we have found period, and we know that period is equal to 1 over frequency, or frequency is equal to 1 over period. So if you put in place, the frequency is equal to 1 over period, which is equal to 1 over 0.3, 3.3 hertz. That means in 1 second, the particles made 3.3 complete oscillations. So we have finished the first part of waves. I think it's enough for today. So we'll continue to the same topic next week. And thank you for listening. See you next week at the same time. Thank you.